Hi, Derju. Nice seeing you here.
Hi. Hi, Doji.
Yeah, nice seeing you here. The students have not shown up yet, so we wait a little while, I suppose.
Okay.
Okay, we just wait one more minute, perhaps, and then we can start the class. Usually students come late, unfortunately.
Okay, no problem.
Do you have any questions before we get started?
I don't have any questions for right now.
What about David? Do you have any question?
No, I'm all good.
You're good, okay. Let's wait one more minute, then we get started. Okay, let's get started then. Today I'd like to talk about the finite difference method, especially the E algorithm. So I will start with primarily talking about finite difference method for time domain, which is so-called a finite difference time domain method. And we talk about finite difference approximation, time stepping or time marching, stability analysis, grid dispersion error, and get into some details about the E algorithm and also the finite difference frequency domain method, and briefly touch on absorbing boundary condition. I don't have time to talk too much about absorbing boundary conditions. So finite difference method is vastly popular because it is very simple. Actually, when I was a young man, I could write a code in one afternoon using the finite difference time domain method and start to produce results. It is that simple if you want to put your mind to it. Once you have that code, you can solve Maxwell's equations as shown here for an optical waveguide. So you have a code that can work from DC to optical frequency, if you want to say it that way. And here's another code that shows the application in magnetic resonance imaging. As you know, magnetic resonance imaging makes use of quite a bit of electromagnetic technology. First, you need a DC magnetic field, and then you have to excite the spins in the human body with RF or microwave, almost microwave fields, about a few hundred megahertz. And then you have to listen to the echoes from those spins using what is called a squirrel cage. The squirrel cage is a bunch of RF transmitters and receivers, and they produce electromagnetic fields that interact with the human body. you have to be able to model these things in order to design the squirrel cage properly with the highest sensitivity and so on. So this method is extremely useful because it can be tailor-made to solve highly complicated problems that we encounter in the real world. There's one thing. Another thing is that this method is very, very simple. As I said before, I could write the code in one afternoon if I choose to do so. Perhaps not at my age, but when I was a young man, I was able to do that. Okay, so let's talk about the finite difference method first. Let me write this down. Say if you want to solve a PDE, a PDE is often encountered in Maxwell's equations, but if Maxwell's equations is too complicated, we look at a simpler partial differential equation, which is a scalar wave equation. Say the scalar wave equation is something of this form. How can we solve this scalar wave equation? The way it is written, the computer cannot talk to this scalar wave equation. We have to convert this equation that can be fed to the computer so as to obtain the solution to this scalar wave equation. And the best approach is to do it with the finite difference method. And we like to approximate the time derivative first. And then approximate the second order time derivative after that. How do we go about doing this? Well, there are very many finite difference methods for approximating the derivative of a function. For instance, if I have a need to approximate this function as its time derivative, I can pick a value or two values that are very close to each other. I can have this function evaluated at a time step t, or at t plus delta t being a small number, and then minus its value at rt, and then divide by the spacing in the time step. This would be an approximation to the time derivative, and this is called the forward difference formula. Such a formula where you use difference to approximate the derivatives is called difference formula. And this formula takes value that is ahead of its time minus the value at the present time to approximate the time derivative. And the second way is actually to do a backward differencing. By the same token, why not use something that is behind its time to approximate this derivative? So you would replace this with t minus delta t, and then divided by delta t. And this is a backward difference approximation. Okay, and then the third approach obviously would be doing something that is in between the two. If I want to approximate this derivative, why not pick something more creative than above 2, which is pick the value of t that is slightly ahead of its time, and then take the value that is slightly behind its time, and then divided by delta t. This is called the central or center differencing. Central differencing might be the better name for it. So there are three different ways of approximating a derivative. This is the first derivative, and I have a picture that shows this. Let me bring this picture closer to my discussion slide. So if I were to show you with this picture, a forward difference formula would look something like this. Given this function, you take a value at the present value, subtracted from the value that is ahead of its time, and then you approximate the slope of this curve. That's essentially what the derivative is. You're trying to find the slope of this curve. And then you can also approximate the slope of the curve using its present value, subtracting that of the value at some time behind. Okay, and this is called a backward difference formula. And the third method is, of course, if you want the value at this point, you take a value that is slightly ahead of its time and the value that's slightly behind its time, and then approximate this slope, and this is called a central difference. Essentially, those formulas are given by such thing. Then you can generalize this idea to taking second order derivatives. So if you apply this method 2 times, if you want a second order derivative, like what you encounter here, then what you do then is to say that the second order derivative, I wouldn't go through the detail, okay, would be the application of the first order derivative 2 times. And if you were to go through the central difference approximation, I'm going to use central difference approximation because it is the best of the 3. And what you get then is that you can show that this is phi r t plus delta t minus 2 phi r t plus phi r t minus delta t. Okay, believe me, if you do this 2 times, you get this formula. And it's kind of tedious to go through this formula, and it's quite straightforward too. Just apply this formula 2 times. The central differencing 2 times, you get this formula. And if you're not convinced, you can go home and try that out. It's very simple. And this allows us to approximate the second order derivative we have in the wave equation, which can be derived from Maxwell's equations. And then we can use a shorthand notation for this as well. Okay, we can use a shorthand notation for this because labeling things this way is kind of laborious. So I'm going to say that phi of t would be labeled with phi of L delta t, because I'm taking a time step of delta t every time. So I use my counter L to count my time step. And then instead of writing something like this, I just write phi superscript L. And that is often encountered in the numerical computation literature. Okay, so if I use this notation, then this can be written as being phi L plus 1 R. L plus 1 means I'm at the forward time step, and then phi L, which is the present time step, plus phi R L minus 1 at the previous time steps, divided by delta t squared. Okay, and one of the things that you have to notice is that if you compare the error you have in these 3 different methods, you can see that this method, the third method, is the most accurate of all, because you can see that the slope that you have is closest to the true slope. Whereas the other 2 methods, as you make the time step larger and larger, you are going to have a departure from the true slope more and more. Okay, so the central difference formula is the most accurate. And you can also show that by Taylor series expansion. If you do a Taylor series expansion of this function, you can show that the error of this is order delta t squared. Okay, the error is order delta t squared. Whereas the error here is order delta t for this method and order delta t for this method. So the third method is the most accurate of the three. And so when you apply central differencing to the second derivative, you can also show that the error by Taylor series expansion is of order delta t squared. So those are the things that you have to take note of with central difference. Okay, so this actually enables us to solve very, very complicated wave equations. For instance, if I have these wave equations that I want to solve that I write down earlier, which can be written as partial square t square phi of r of t is equal to c square. C can be a function of position, which means that the medium can be very complicated. Okay, and then I can apply the finite difference approximation to the left-hand side. If I do that, then I would see that the left-hand side can be written as 1 over delta t square. Remember that we have a delta t square from the second order difference approximation. Okay, and then phi L plus 1 R minus 2 phi LR plus phi L minus 1 R. And then that will be equal to C squared times this phi LR. Okay, and now I can rewrite this formula in such a way that it is more suggestive of a time marching or time stepping. Okay, how do I do that? Then this is a field that is future in time. This is the field that is at the present moment. This is the field at the past time, a step behind time. Okay, so I can rearrange this equation so that whatever I need that is ahead of time can be put on the left-hand side, and then I multiply the c delta t across, and then take whatever I have in the past time and put it on the right-hand side instead of the left-hand side. And then the delta t gets multiplied across, so I have this thing. I have this equation. This equation is beautiful in the sense that it says that if I know the present time of the field, if I know the past time of the field just one step behind, and the present time of the field in the space, and if I know how to compute the right-hand side, then I can use that to predict what the field would be one step forward in time. Okay, one step forward in time. And that is wonderful. I can keep running this code or running this numerical code. And then I can start with some initial value of the field at some past time and step forward in time so that I can get the time, the field for all times. Okay, I will get the field for all times. But then there's still a question as to how do I evaluate the right-hand side? I can evaluate the right-hand side approximately as well. And this area, usually we use a very simple method to evaluate the right-hand side. Simplicity rules in this method. We do not want to deal with complicated methods. Okay, rules is used as a verb here. Okay, simplicity rules. So I would like to find a way to evaluate the right-hand side. So I have put the time on the metric, which is time stepping. I also would like to put the space on a grid point. And if I do put this grid point to represent this field, let me do a 2D illustration of this thing. Okay, 2D illustration. If I want to have this field in 2D, the field would be a function of x, y, and L. Okay, for a given time step, I would have this field being displayed as a function of x and y, and I can put them on grid points. As I have shown here. And once you have put the field on a grid point, this grid points might be labeled as, I can also do the same thing and say that this is like L delta x, M delta y, for instance. I can put them on the grid point and label them as such. And then if I am able to have this field evaluated on a grid point, I can also approximate the derivative of this field in the x direction, the derivative of this field in the y direction using finite difference formula. Okay, so that means that I would be able to evaluate this Laplacian, which is just, for instance, in this example here, given by this. And I can use finite difference approximation to evaluate the right-hand side. And then having done this, the field value in 2 dimensions will be written as phi m, in this case, L, m. Sorry, I shouldn't use an L here. L is no good, okay? L is also used for time. So I should use m and n. Then the field value can be denoted as phi mn and store them on the computer. Okay, I can store this number on the computer, and our computer will be stored as such. And these are points like m is equal to 1, 2, 3, 4, and then n is equal to 1, 2, 3, 4. Okay, so I have discretized space both in the x and the y direction, and store the data, the field value at each of these points as a data point. I can store them on the computer. Then I can use these data points to evaluate the derivatives of the field using a finite difference approximation, including its second order derivatives. And then I would be able to evaluate the right-hand side. And once I know how to evaluate the right-hand side, I can use this for time marching or time stepping. Are there any questions regarding this? What is time marching and time stepping? So it is a very simple concept with no deep mathematical knowledge needed. What you need is just high school arithmetics. And the other friend that you need is a dumb computer. If you can program the dumb computer, they can work at breakneck speed, and then they can actually compute this very, very quickly for you. So are there any questions regarding this time marching method? Well, this method is useless unless it is stable. That is, as you march forward in time, the field solution is bounded and does not grow with time. So the next important notion that we have to understand is the stability, okay, stability analysis. So the next thing I like to do is actually to perform stability analysis of this method. So I assume that I have done an approximation to my scalar wave equation, and then I would have approximate my second derivative using finite difference method. So what I have is that given this wave equation that I have, let me write it down. RT is equal to the Laplacian of phi RT, then I can use finite difference approximation to the left-hand side. I also need to make finite difference approximation for the right-hand side, which would be amounting to that if I have the x derivative, for instance, of this function phi x, y, z, and t, it would be amounting to, actually, if I use the finite difference notation, I will evaluate my phi at one grid point over, and then at the NP grid point at the present time step, minus 2 phi at the present grid point at the present time step. Okay, and then a neighboring grid point, because this is a second order derivative, it will be m minus 1L NP. So it's that simple. That's why you can program a code in one afternoon if you're set to do it. So this second order space derivative is written as such. I can do that to the y derivative as well as the z derivatives. Then I would have the same thing done to the left-hand side. And I like to approximate, I like to ascertain how big the error is when I approximate things with the space derivative as such. Okay, let's see what happens. So in order to do stability analysis, I assume that I have a plane wave solution, that my phi x, y, z, t is of the form of a plane wave. It's proportional to e to the I k dot r. I can even put I omega t in there if I want to. Okay, let's assume that I have a time harmonic plane wave passing through the medium. And let's assume this to be my trial solution. Okay, my trial solution. And now if I were to approximate this on the finite difference grid, then you can see that what you have here is that it would be, let me lump this together. Delta t with an L, there should be an L here, L delta t. Okay, so if I have replaced this with m and p, this will be L delta t e to the I kx m delta x plus I ky n delta y plus I kz p delta z. Okay, can everybody see that? That if I were to put this plane wave on the finite difference grid with finite difference approximation, then my field value would become such a function. And I'm going to call this part just a to the power of L to save writing. Okay, that is just a to the power of L. And then what I have then is that if I were to plug these approximations in there, I will see this very interesting thing, which is that partial square, partial x square, phi will be given by this. And if you plug in the x variation into this thing, you will find that this is actually equal to, if you plug in this variation, you're going to see something very simple. It would be something like, since only delta x changes, okay, you will pick up a term like I kx delta x minus 2 plus e to the minus I kx delta x. And then you put this thing out there again, m and p. Can you see that? what happens is that if you plug this into this finite difference approximation, only m changes as you go from the left to the right, because only m changes on this term change. This becomes m plus 1, m minus 1, and then you can have a increased phase term for the first term. The term in the middle that does nothing, the phase remains the same. And in the third term, which m minus 1, you have this other term. And then you can pull the whole factor out again out of this approximation. So if you think about what this is just, you can combine the two to make like a cosine. This term combined with this term becomes a cosine. So this is actually 2 cosine kx delta x minus 1. Okay, phi MNPL. And if you are very good in trigonometric identities, you can write this cosine as a sine. So it becomes 4 sine square kx delta x over 2. Okay, I won't go through the trigonometric identity exercise. You have done that in high school. Okay, you have done that in high school and you know how to do that. You can do that at home. Then I repeat the same thing for the y derivative, because this thing has 3 derivatives: partial square, partial y square, partial square, partial z square. Okay. I can repeat the same for the y derivatives, and then I will have a very interesting formula. Okay, I will have a very interesting formula that the right-hand side of this, after making the finite difference approximation, becomes something like 1 over c squared. I haven't made approximations to my time derivative yet. And then I would have something like minus 4 over delta s squared. Because I have missed a because when I do this, actually I need to divide by delta x squared, and I have missed that in this approximation. So I should go back and put that back in. So because it's the second derivative, I'm missing this delta s squared. Because when you do the second order approximation, you should put that in. So if you do that to all the 3 terms on the right-hand side, the correct formula you have now is sine square kx delta x, and I'm going to call delta x, delta y, delta z the same. Okay, I'm going to call delta x equals to delta y equal to delta z, and all of them I'm going to call them delta s to make things simpler. So the second term for ky, I still use delta s. Okay, and then the third term is for kz, I still call it delta s. So, and this is what you have, and then you have to multiply this again on the outside here by phi MNPL. Okay, you have to multiply by this. But this is the consequence of doing this analysis to each of the term. Okay, and then I have put in this delta x squared, and that gives me delta s squared over here. Okay, so believe me, this is what you get of the right-hand side. This is the consequence of finite difference approximating the Laplacian of this field. Okay, you get something like this. And why are we going through this careful analysis? Because we want to find out how good the finite difference approximation is. So we have to do further and see how good the finite difference approximation is, and when it would be stable. Okay, when it would be stable. And then I'm going to do the left-hand side now. Left-hand side, I'm going to use a time stepping approximation or finite difference approximation in time. And if I were to convert the left-hand side in my notation for finite difference method, so I would have something like this for the left-hand side. So this is what becomes of the left-hand side. And of course, I shouldn't forget my delta t squared. Okay, this is what becomes of my left-hand side. And then I'm going to plug this in there. Okay, I'm going to plug this in there. Plug this in here, but with time changing. So only the first term will be affected. Okay, will be affected. And so if you believe me, if you plug this in there, only this first term will be affected because I'm doing a finite difference in time. So let me just use this shorthand notation to denote what is happening. Then this formula just becomes, left-hand side just becomes 1c squared delta t squared. And then what I have then is that using the notation for the amplitude, I would a l plus 1 minus 2 al plus a l minus 1. This is what becomes of these three terms. And then I can pull a common term outside. Okay. And the left-hand side will become as such. And I'm going to assume that al plus 1 is going to be a g factor times al. And remember, my al is actually just this, if you recall what my al is. My al is frequency domain wave function. And if I put it in the finite difference wall, this al is just equal to that. And then the g factor, of course, I guess if I can write this down more explicitly, it will be a0 e to the minus I omega L delta t. And you can see that the g factor here is just e to the minus I omega delta t. Okay, this is my g factor. So the g factor in general would have a magnitude of 1, which is wonderful. If it has a magnitude of 1, that means that it is non-amplifying. That means that as I advance in time, the amplitude of the wave function will not amplify in time. And so if g has to be 1, then it implies that omega is real. So the mode, the Fourier mode that you're putting through the system has to have a real frequency. If, however, you choose your grid size and the time step in such a way that omega becomes a complex number, then g is not guaranteed to be 1, and then you will have amplification. In that case, if omega is a complex number, then g would have an amplitude other than 1, and you have amplification, which gives rise to instability. So let's do this more carefully. And you plug this in there, okay, plug this into the left-hand side. What equations that you have is that the left-hand side will become g, the first term is just g, okay, minus 2 plus g inverse al. That's what happens to the left-hand side if you plug this in. And then it should be equal to the right-hand side. The right-hand side will be this very complicated function. Okay, let me just call this s squared for simplicity. Let me just call this s squared for simplicity, and then the right-hand side would just be, I hope I get everything correct here, for delta t squared over delta s squared. I'm assuming all space steps to be the same, s squared al. Okay, the right-hand side would just be that. My s squared is this sum of three sine functions, and this can be canceled. And you can now solve this equation. You can solve this equation, and you can write this equation even more simply as being equal to minus 4 r squared s squared. Okay, where s squared is that, then r is just this ratio. Let me see, am I missing I'm missing a c somewhere. Okay, there's a c somewhere lurking around that I have dropped. Okay, so there is a c somewhere. Let me put the c back in here. So r is c delta t over delta s. Okay, so then you can solve this equation very easily and figure out when g would have magnitude of 1 and when g would have magnitude not equal to 1. And this is just a quadratic equation that you learn how to solve in high school. I even don't remember those quadratic formulas by now. If you use a quadratic formula, you can show that the roots of this equation is given by this formula over here. Okay, so the wonderful thing is that if Rs is less than 1, this becomes pure imaginary. This term becomes pure imaginary. And then you have the real number plus an imaginary number. And you can find that amplitude of that real number plus imaginary number quite easily using your knowledge of how to find the amplitude of a complex number. And you have this very interesting criterion that you can arrive at. Okay, the criterion is that if Rs is less than 1, then what you have is that this number becomes an imaginary number. And if you find the amplitude of these two, there are some cancellation of terms that the amplitude of G becomes actually 1. I will have time to show that this. It can be shown by high school algebra. You can show that amplitude of G equals to 1 if Rs is less than 1. Okay, and so if Rs is less than 1, G would be equal to 1. It means stable time stepping. Okay, stable time stepping, and then you can go back and look at what G is. G is just that factor over there, and Rs is that very complicated factor over here. Sine is just this very big sum of 3 sines. Okay, and then you can actually figure out that this is actually my big S. Okay, S is always bounded by 3. Because S is the sum of 3 sine functions. It can never be larger than 3. Okay, so if my Rs is less than 1, it means that my R must be less than 1 over S. Okay, but what is my R? My R is intimately related to my time step and space steps. Okay, R is just the ratio of my time step to my space step times C. And if you work this out, and you might have to wrap your brain around this a little bit. Let me write down what R is. R is C delta T over delta S. Okay, that is what my R is. And then, so if S square, if S is less than 3, let me see, sorry. S square is less than 3, not S. Okay, S square is less than 3. So if I look at this condition, then I arrive at the stability condition that this thing, okay, this thing 1 over S is always larger than 1 over root 3. Okay, because S is bounded by 3. So 1 over S will be bounded on the left-hand side by 1 over root 3. And so if I ensure that my R, okay, if my R is bounded by 1 over root 3, then these conditions will always be satisfied. If I ensure that R is less than 1 over root 3, then R is definitely less than 1 over S. And if R is definitely less than 1 over S, this criterion is satisfied, and then I will always get G equals 1. So if I write this out more explicitly, this says that C delta T must be less than 1 over root 3 times the space step if I plug in the value of R. And this gives you a very interesting notion. It says that C times delta T is the distance traveled by the light in this very small time step. And if this distance traveled by the light in this very time step is less than delta S, the space step, then I have stability. And you can figure out what the 1 over root 3 means, actually, because I'm doing this problem in 3 dimensions. I have 1 over root 3. But if I do this in 2 dimensions, I will have 1 over root 2. And if I do this in 1 dimension, it will be just 1. What it says is that you can imagine a grid point. And then this grid point has some lattice front, okay? And if you can figure out the distance between this lattice plane, in 2 dimensions, it will be 1 over root 2. In 3 dimensions, it will be 1 over root 3. So 1 over root 2 and 1 over root 3 are the distance between lattice planes. Okay, let me write it down, lattice planes, that you can fit through the finite difference grid. And if your time step is less than that time, the time needed to travel through that lattice plane, then you have stability. This kind of stability is also called the CFL, stability analysis, or Courant Friedrich lever stability analysis. Okay, are there any questions before we move on? So I would not go through the grid dispersion error analysis. That is, you have to have your time step been small in order to get a stable solution, but you can also have to have the space step been small. And that is done in the lecture note. It's kind of intuitively obvious. You cannot make a very crude finite difference approximation of the wave equation, for instance. If you were to make a very crude approximation of this thing using a very crude, that should be actually a 1 over delta x squared here. Okay, if I do this correctly. And if you make a very crude approximation of the space derivative, you're going to have large errors too. Those errors are called the grid dispersion error. Okay, I'm not going to go to the analysis of grid dispersion error. It's done in the lecture notes. It's kind of natural to expect that there are such thing as a free lunch. You cannot make the grid point arbitrarily large, because if you make the grid point arbitrarily large, you can take large time steps, and then you can step through the solution very quickly as if you have a free lunch. That doesn't occur. Okay, so I like to talk about the Yi algorithm a little bit. Yi algorithm is a way of applying a finite difference time domain method to approximate the time derivatives as well as the space derivatives. And it was proposed by Yi in 1966 and made popular or popularized by Alan Tafloff of Northwestern University. You can think of it more abstractly as a way of time marching these Maxwell's equations, okay? And it's also described in greater detail in the lecture notes. So what you do then is actually to put the field, the E field, on a rectangle or square like this, and then put the H field on the face of this rectangle or square. And then you do that for all the 6 faces of the grid. And then you will find that the E field and the H field are in staggered grid. Okay, this is called the E grid. E and H are staggered. Okay, you can see that the curl of E give rise to H, and then you can trace the H. I don't have a big picture of it, nice picture of it. You can think of the H as going around, and then it produces the E. So this E grid replicate this physics really well. Okay, curl of H is d dt plus J. So you can see on this grid, curl of E gives you H, and then curl of H, if you can trace the H field going around, give you E. And this Maxwell's equations is replicated in a very intuitive fashion. And then you can actually write down the code in one afternoon if you have the grit or the will to do that. And with this kind of code, you can feed it to a supercomputer and generating interesting plots like this. Okay, I am running out of time. I hope you enjoy this simple and wonderful technique, and maybe someday you, just as a hobby, sit down one afternoon to write a code to solve Maxwell's equations. Are there any questions? No questions. Okay. So the test of the pudding is actually to put this to practice. And if you want to practice this, I don't have time to give you a long homework, but maybe after the semester is over, you can go and practice this yourself. Some very simple examples. Okay, I'll let you go then. Thank you for coming.
Thank you.
Thank you. Bye-bye.